Okay, here we go. The correct answer to this should be 39 halves, not 29 thirds. Just inverted some digits there. The interval goes from -1 to 2. So each equal subinterval will be the length of that interval from -1 to 2, which is 2 minus a -1 over n, or 3 over n. That's delta x. Then we're going to start at -1. Think of it as a number line. And x of 1 is going to be one of those widths away from -1. That's what we mean right here. X of 1 is -1 plus 1 width. X of 2 is -1 plus 2 widths. So here's x of 2. We've got 2 of these 3 over n's. And by the time we get to the ith right-hand endpoint, we've started at -1 and added on I of these 3 over n. So there's an expression for the right-hand endpoint. And now what we want to do is come up with a formula for the area of the ith rectangle. So we plug this number into the function definition, or this expression into the function definition, and multiply by the width of that subinterval. And then we're going to add all those areas together and let the number of rectangles approach infinity. So here's what we start with right here. Find the limit as n approaches infinity of the sum of the areas of all these rectangles, n of them. So here's the x of I plugged into the function. We got to square this, plus x, that's the right-hand endpoint, plus 2, and here we've multiplied by delta x, or the width of the rectangle. So this expression right here is a formula for the area of the ith rectangle. But we're going to add those up that many times. Okay, but we're going to take the limit as n approaches infinity. Now here's what you get if you simplify all that. Square this binomial, combine similar terms, distribute the 3 over n, and this is what you get. Okay, and now we're going to use some theorems on summation notation to kind of distribute the summation notation times each term inside the brackets, moving constants out front. So this term right here will become 15 over n. N is just a constant, so I can move that out front, times the sum from I equals 1 to n of just a 1. That's all that's left from this term. Move this constant out front, the -63 over n squared, times the sum from I equals 1 to n of I. And the third term, 108 over n cubed, goes out front. Sum from I equals 1 to n of I squared. And these are well-known formulas. So I can replace sum from I equals 1 to n of I with n times n plus 1 all over 2. And the sum of I squared is n times n plus 1 times 2n plus 1 all over 6. Oh, by the way, I dropped off the limit as n approaches infinity from all of these. So there's the replacement. And now it's just a matter of algebraically simplifying and then taking the limit. So this summation has a sum of n, so n times 15 over n is just 15. If you picture distributing n over n plus 1, you get this. Interchange the 2 and the n squared. Same deal here. Move the 6 here and the n cubed here. If you picture multiplying these factors all together, the leading term is going to be 2n cubed. The rest of them we're not really going to care about, because when we take the limit as n approaches infinity, those terms are going to become 0. 2n cubed over n cubed as n approaches infinity is just a 2. That's why what we really get is 15 minus 63 halves. This should have been 108 thirds, not 6. I got carried away. Because this 2 cancels into this 6, leaving a 3. Okay, and then if you get a common denominator, combine these all together, and reduce, you get 39 halves. I'll let you double check that. Okay, hope that helps. If you have any questions, post a comment.